Hello, everybody, and welcome to this one of the final lectures in the course. There are a few left. In last week's lectures, we showed that every Lie algebra every finite dimensional Lie algebra could be described as the semi-direct product of a nilpotent and a semi-simple Lie algebra. Okay, this now, for the last couple of lectures, we're going to show that there's an amazing classification of semi-simple Lie algebras. Okay, this is not something that holds for nilpotent. For nilpotent, it's quite mysterious and much more difficult. But for semi-simple, there is an amazing classification, and this classification is expressed in terms of things called root systems. And that's what we're going to discuss in this lecture. So actually, we're not going to discuss anything. We're not going to mention, well, we're not going to use any of the properties or any of the definitions that we had before about Lie algebras. We're going to start from zero. We're starting again, tabula rasa. So if you got completely lost before, this is a good place to re-enter. But then in the next lecture, what we'll do is show how every semi-simple Lie algebra gives us a root system. And in fact, these root systems are in bijection with the semi-simple Lie algebras, meaning that if we classify root systems, we're actually classifying semi-simple Lie algebras. Okay. But maybe let's, because these are fun, maybe it's easier to start with the root system and afterwards show the correspondence with semi-simple Lie algebras. Okay, so what is a root system? In this lecture, we're going to be basically talking about real vector spaces. So before we were talking about very general fields, even finite fields or fields, and we were working with general fields and then afterwards imposing certain conditions like algebraic closure, and characteristic, and so on and so on. Here we're just dealing with the real numbers. So we're going to take E, which is a real vector space, and we want it endowed with an inner product. So before, again, we were talking about symmetric bilinear forms and so on. Here we're dealing with something much simpler, just a plain ordinary inner product. Now a root system is going to be a finite subset of the real vector space. Okay. And we call the elements of this finite set roots. Now, it's not a finite dimensional subset, not a finite dimensional subspace, but it's just a finite collection of vectors inside there, satisfying certain conditions. And the first condition is, however, that the vector space that's generated by this finite set is in fact the entire vector space. However, you should not look at this and think, it's some type of basis. It's definitely not some type of basis. These vectors will not be linearly independent in general. They will not be linearly independent, actually. Okay, that actually comes from, you can see here from the last condition, we'll see that they will not be linearly independent. So it's something different from a basis, okay? And you should probably try to leave your intuition from vector space basis here, because these are different things. They feel very, very different. First, the second condition, one which might seem initially a little bit artificial, is that you're asking that this quotient here is an integer. This is contained inside in Z. Okay. So what we're doing is and this is for any two roots, alpha and beta, contained in our root system. So we want to take the inner product of alpha with itself, it's like the square of the norm, and then we take the inner product of alpha and beta, we divide one by the other and we multiply by 2, and you want this to be an integer. Where are we coming up with this? It seems, where is this arriving from? I mean, why could it not be 3, 4, 5, 6 and so on? The reason why this strange, some almost arbitrary looking number is appearing here is actually, you can see it more naturally from the third condition. So basically what we want, and this is like, maybe it would actually be more natural to put this as 3 instead of 2, but it's maybe more standard, is that we want our root system to be closed under reflections. So the symmetry here is that's something that's different from a basis. You have this amazing symmetry going on in a root system, and that's really what's going on. So it's a finite subset of elements of your vector space that are closed under these very special symmetries. That's really what's going on. The symmetry of the root system is at its heart. And you can almost take this to be the main condition. So what are we doing? We're taking any element in our root system and we're defining a map from the vector space to the vector space. Okay, how are we defining it? Well, we take our elements, general element in E, we map it to itself minus this. You see, this is the same. Sorry, there were brackets missing here. You write those in. This should be a bracket and this should be a bracket. This quality here, you see, is what's appearing here. That's basically where this comes from. But why does this appear? Well, if you see, this is basically just reflection in the hyperplane orthogonal to alpha. So if you sit down and look at an example, see what this is, that's really what it is. You're reflecting. You've got a vector, your vector is going to determine, right, but all of the elements perpendicular to it, determine then one of a hyperplane, which is to say a subspace of codimension 1. And then you're taking reflections with regard to this. Okay, and that's where that comes from. That's where the 2. It's because basically, if you alternatively think about take your alpha, then take the hyperplane perpendicular to it, take a basis of this, an orthonormal basis of this, and you'll see that if you do that, then basically when you expand alpha in terms of this orthonormal basis, this quality here is going to be 0 for every term except for lambda sub alpha by alpha, when then this gives the coefficient in the expansion of lambda with respect to this basis. Then we're going to subtract this. So we take out the piece that's already there, and then we add in another negative one. That's where the 2 is coming from. We're subtracting the component that's already there, and then adding in another one, giving you 2. What that does then is just gives us a reflection in that component. It leaves everything else the same. It gives us a reflection in this component. And that's what's going on. This funny quality here, this funny number, is basically just a mathematical description of reflection. It's just maybe more intuitive if you look at it visually. And that's why it looks artificially, because we're writing it down, I guess, in symbols, writing it down in equations, as opposed to looking at it in terms of a picture. But because these things are arbitrary dimension, it's difficult to do that. So we have to rely on these. And then it's asking that the second condition you can then see is basically asking that the symmetry that we have here, this symmetry under reflection. Oh, sorry, there's another, wow. Yeah. So we've defined this reflection, and then it's asking, there's a condition missing here, most important one, is that when we take any root vector, and then we operate on the roots by this reflection, then we're going to land back inside in this. So it's basically that the reflections permute. The reflections are going to permute the roots. That's the symmetry condition that we're imposing. So the symmetry group that we have is generated by these guys. We ask that it gives a that it lives inside the automorphism group, that it restricts to the automorphism inside the automorphism group of the roots. Then this condition here is basically asking that these symmetries are somehow integer symmetries. And this becomes a little bit more natural. So these root systems are basically everything is sort of integer based. And then finally, we have this condition, which, well, it says that the only multiples for any root alpha, the only multiples of alpha that you get inside the root system are plus and minus alpha. So there's no real scalar structure on this where you can multiply by any scalar you want. This is absolutely not true. You can only multiply by plus and minus 1. Okay. So it's definitely not some kind of, well, of course it's not a subspace because it's finite dimensional, but there's no scalar action here, just by plus and minus 1. So it's quite a finite thing. Okay, so Move on. No, some remarks. Let's just try to explore the definition a little bit. Well, if we take alpha s like this, we operate on alpha by alpha, we're going to end up with alpha minus 2 alpha, which is minus alpha. See from here, it's going to be alpha, it goes to alpha minus, and then these two things will cancel because it's bracket, it's the inner product of alpha and the inner product of alpha and alpha, they cancel. So you end up with minus alpha. So this preserves, alpha is going to preserve this vector. Or sorry, it doesn't preserve the vector, it sends this vector to minus 1. It's the reflection in this part. Fixes the hyperplane, as you see here. So if alpha and lambda are orthogonal, so you have something living in this orthogonal hyperplane, then, which is to say, in symbols, we just mean this, orthogonal with respect to the inner product, then nothing happens. Because the correction term that you have, this minus 2 bracket term, this is going to be 0 because the numerator is going to be 0. So there's no correction happening here, so it just goes to 0. So then you see maybe more concretely written in terms of equations what I meant before by this reflection that's going on. So that means that we can interpret alpha as reflection with respect to this hyperplane. Okay. It fixes the hyperplane and then it flips the alpha and acts linearly on any linear combination of elements. Okay, we also know that S squared is going to be equal to the identity. This you can check, but it's easy. So that means in particular that these things are automorphisms. Sorry, this is another misprint. Let me see, that should not be S. That should be 2 S squared. You apply it twice to get back the 60. You can see that from here, I guess, because here it's just going to be the identity. So if you take it on something here, well, it just gives you back lambda. So if you do it twice, you get back lambda. Here you get minus alpha, and then operating again, you're going to get minus alpha. And then it's going to be the identity on this component, the identity on this component. So the identity on the whole thing. Okay. So these things will form a group as we see later on because S squared is equal to minus 1. Let's clear the drawing. Now, what's an example of these things? Well, this is probably one of the easiest examples. Let E be the vector space. So it's going to be those elements inside an R to the n plus 1, such that when you add up the terms inside here, so we're writing this as x is equal to x1 up to x to the n plus 1. All right. And then when we add up, we take the sum of all of these, and we endow it, of course, with the restriction of the usual Euclidean inner product in R to the n. Then we're proposing that this finite subset of vectors is actually a root space. Okay, so we have to check. We have to check that it actually spans the whole space. But this, I think we can see. Remember, it's not going to span R plus 1. It spans all of those vectors such that their sum goes to 1. And well, you can, if it's not immediately clear, think about it for a while. Look at some small examples, and you'll see that actually it does. You can always take linear combinations of these E minus 1 so that they will work. Or maybe the easiest way to see it is if all of that means that this last term here has to be equal to minus the sum of all of these guys. Okay. And then all you need to do is take, then from this, it's clear. Okay. So that's the first condition, that it spans, that this works. We also see that the only elements that are inside here, the only elements that live inside here are, if I multiply this by -1, okay, so minus ij is equal to alpha ji. Okay, so clearly plus -1 is going to be contained inside there. But not for anything else. If you multiply by any other scalar, it's not going to be contained inside here. Okay. So that one is okay. Also, the integer condition, the sort of strange integer condition, this is satisfied. Okay, because you see these are the only possibilities. I mean, it's just the basic inner product. You see that if both these vectors match, then we're going to get a 2. If only one of them matches, well, if the first and the second match, then we're going to get a -1, and the same with the second and the first. And if it's only these guys, and so on, you can see what's going on. So we're always going to get an integer like this, and then the 2 is going to cancel here with the 2, and so on. So this, just by direct checking, you can see that this is going to be this will always be an integer. Okay, so that's that satisfied. The last one is that it preserves, and the most important one is that it preserves the symmetries. So let's look and see how that works. Well, just write out the reflection for alpha sub ij operating on a general lambda, and you see we get this. What does that mean explicitly? Well, if you look at this, carefully write it out, you'll see that what it does is it just takes, for a general lambda, we take the ith term and the jth term, and it just flips them around. That's really all this does. Okay, and then from this, you can see, think about it if it's not clear, it's not very difficult, is that it will actually always send roots to roots. So it will always send some alpha j to some alpha kl, depending on how the i's and the j's match with the i's and j's in the root that you're looking at. But it has this symmetry that preserves, that gives us a symmetry of the root system. All right, and we call this root system a to the n, a sub n. All right, so that's the first example, a very important example. And most of the root systems actually look like this. They're going to be some finite collection of vectors given in terms of the usual basis of an ambient space in which it lives. They'll actually, all of them will be some variation on this, as we see. Okay, so now let's try to prove something else. Another basic consequence. If we have any two roots that live inside in our root system, such that alpha is not equal to plus minus beta, and without loss of generality, let's just, one of them will be bigger, possibly they're equal, the norms, the size of them, the length. That's going to be just alpha. This is of course just equal to the square root of the inner product of beta with itself, and this is just equal to the square root of the inner product of alpha with itself. One of them has to be less than the other, or they're equal, or one of them is less than the other without loss of generality. Let's assume that alpha is the greater one. Then let theta be the angle between them. So what I mean by that is you have the two vectors. So the two vectors inside in this larger Euclidean space are going to form a plane. And we want to see the angle between these two vectors in that plane. What this says is that we only have the following possibilities. So this is really how, I mean, because there's the symmetry and you begin to think more geometric thinking, and you look at the shape of the possible root systems is somehow determined by the possible angles between the root vectors. Okay, and the claim is that we've one of the following 7 possibilities. So it's saying, we're taking, sorry, there's a slight mistake here as well. So this should actually be the square bracket. And the square bracket is going to be, so if I have alpha and beta, then alpha by beta is going to be equal to, it's just this magic formula again. And alpha. Okay, so it proves useful to, and this is just a definition, proves useful to actually have one symbol to describe this because we use it quite often. Notice that this thing is not symmetric, okay? Because if I put the beta here first, then I'm going to have a different numerator. I'm going to have beta by beta down here. So it's not symmetric, and that's why we see here that this is not symmetric. So the possibilities are for beta alpha 0 and alpha beta 0, 0, which is to say the angle between them is pi over 2. I can have a 1 and a 1, the angle between them is pi over 3, minus 1, the angle is 2 pi over 3, and so on and so on and so on. So it sees that actually this definition of a root system is quite rigid. That's why we're able to classify these things, because these abstract conditions, which may initially seem quite general, are actually very, very restrictive. That's the first sign. We see that these are the only possible angles that we can have on the plane determined by these two vectors. So let's prove this. So we consider two integers. They're going to be just this is again, you should see this is the angular bracket of alpha and beta, and this is the second one is the angular bracket of beta and alpha. We're taking n and m. Now, in general, you know from your elementary coordinate geometry, I guess, that when you have an inner product, the Euclidean inner product, that's going to be related to the angle by the norm of the two vectors you're looking at, alpha and beta. Basic identity. So from this basic identity, we see that multiplying n and m gives us 4 by the inner product of alpha and beta squared over the norm squared, which is just to say the inner product of alpha alpha and the inner product of beta beta, and then that's equal to 4 cos squared theta. Okay, just from this identity here, bring this below. Now, by assumption, beta and alpha are not going to be related by plus or minus 1. So that means that the cos theta can't be 0, because if these things are the same or perpendicular, which is to say if the angle was going to be 0 or pi, then the cos of that corresponding angle would be plus or minus 1. But that's not the case. So we can exclude the possibility that cos is equal to plus or minus 1. So cos will have to be between 0, will have to be greater than or equal to 0 and strictly less than 1, the norm of cos, or the square of cos equivalently. So that means that n and m must be contained in 0, 1, 2, or 3. Okay, we've got this number here, this cos squared, something which is strictly greater than 0, greater than or equal to 0 and strictly less than 1. And when you multiply it by 4, you get an integer. Well, the only integers contained in this are going to be 0, 1, 2, or 3. Basically, the point is that we've excluded 4 from this condition here, because this condition implies this excludes 4. Now, if we take n over m, then we're going to get the inner product of beta with itself. Sorry, there's a square missing here. Okay, n over m is equal to beta beta over alpha alpha, because we've got a cancellation occurring between this, and the 2 and the 2. These are equal to, and we know then by assumption that alpha, the norm of alpha is greater than the norm of beta, greater than or equal to. So we know that this is less than or equal to 1. Hence, we know that the absolute value of m is going to be less than or equal to the absolute value of n. Now, if m is equal to 0, then n is equal to 0. If m is equal to plus or minus 1, then n is going to be equal to plus minus 1, plus minus 2, plus minus 3. And the angle theta is determined from the identity, then just going back, theta squared is equal to this, just some basic trigonometry. So that's it, a very elementary proof as we can see, but it really restricts the angles that we can look at. So let's get rid of these drawings and move on. Now from these, we're not going to go through it, but if you want, from this table, one can actually, just with a little bit of hard work, one can show that the only root systems of rank 2, which is to say the only root systems living inside a two-dimensional vector space, are the following. So we've got this cross that's actually equal to the direct product of the root system A1 and A2. I didn't say how to take products of root systems, but there is a natural way to do so. This is the root system A2. Okay, so if you remember these EIs minus EJ, EI minus EJ, the root system given by this represented, just writing out what these vectors are inside an R2. Let me write this here. Everything here is living inside an R2. Of course, at our usual X and Y axis. And it looks like this. That's what A2 is when it's written out visually. Maybe it's easier to see it like this. Then you can also see that the reflections, so if I pick one particular vector, for example, this one, then when I reflect, it's reflection around this, it's reflection here. So then this gets it's reflected to this and vice versa. Okay, and this gets reflected to this. And these guys just obviously will be reflecting around this axis, so they get sent to themselves. Over here, we can see the same, and we can possibly reflect just in this axis, for example. Then we have the symmetry here. This is mapped to this maps to this, and these are reflected to each other. I mean, alternatively, I could just reflect around this axis, for example, and then this would go to this would go to this, and then these would map to each other, and so on. Here, it's exactly the same thing again. You see drawing a line anywhere. Clear that. Drawing a line, for example, here in G2, it's a more complicated one. Again, we see the symmetry. And note that the reflections bring arrows to arrows of the same length. It sort of preserves, the reflections preserve the length of the arrow. It's important. But that's it. So if we restrict the dimension of our vector space E to be 2, then that's it. We just get 4 of them. And as I said, you can actually sit down and conclude that yourselves with some hard work, a little bit of ingenuity from this result here, description of the angles. And that's where we get the first, as I said, we're interested in root systems because they actually correspond to semi-simple E algebras. From every semi-simple E algebra, you can construct a root system. And then it turns out that looking at it from this different point of view from a root system, the classification starts, you start to be able to see that there's a finite number of them for each dimension, for each rank, which allows you to classify things, which allows you in turn to classify semi-simple E algebras. That's what's going on. Okay. Now let me remove those drawings. Clear. Now, let's prove a technical lemma, which is good, a good exercise in the axioms of these root systems. So suppose I have 2 roots, alpha and beta, living inside and 2 roots, alpha and beta. Then in general, when I add together, so this root system won't be closed under addition or difference. That's not true in general. When you add roots together, you get roots. Remember, it generates the whole space, so it's quite easy to take a linear combination of root vectors and produce something that's not inside there. It's kind of, it's special when you have 2 roots and you can take their difference or their sum and actually land again inside the root system. This gives us a criteria for this to happen. So if the inner product of the 2 of them is greater than 0, then their difference will be inside in the root system. If their inner product is less than 0, then their sum will be. And I won't prove it here because we don't really have time, but it's also true that if alpha and beta are perpendicular, just to say if this is equal to 0, then alpha plus minus beta will not be in delta. Okay, this is not true. Okay, something has gone wrong here with the tech. Okay, so I just wrote that in by hand. Let's just take m and n as they were in the notation we used in the proof of the classification of the possible angles. Okay, so we know from the fact that the inner product is 0, then of course the definition of this will also have to be 0. It's just going to be a scalar multiple basically of this quantity. So both these things will have to be equal to 0. Then we go back to the table that we had. So if m was equal to 1, then what we're going to have is alpha minus, this is m. Oh, sorry, that shouldn't be there. That shouldn't be there. Then this is 1, so we get alpha minus beta, but we know that the root system is closed under reflections. This is in the root system, so that means that this is in the root system, and we're done. Now here, this is n. So if n is equal to 1, let's say this, then we're going to try to use the same argument. We want this to be equal to 1. But what do we do here? Well, we just switch this around. So we see if we switch the alpha and the beta as they are up here, then the beta goes here and the alpha turns into this and we get this quantity. So remember, one of them will have to be equal to 1 if you go back to the table. And then we see from this argument here that we get both of them right there. Finally, we observe that this can be obtained from this immediately. Okay, so that gives us both of them. Okay, so that's basically a criteria. Remember that what's the point of all of this? Point is that you can't add together or take sums or differences of root vectors in general. You will not be inside the root system again. But if the inner product is greater than 0 or less than 0, you can take a difference or a product depending on the sign. But if they're perpendicular, as I said, without proving it, then they will never, then the sum or the difference will never be inside there. Okay. So we now come to, as I said, the root space was not a basis of the vector space. You had linear dependence amongst the elements of your root space. You could see this if you go back to let's go back. If you look at this here, you see these are not linearly independent sets because we've got far more elements, far more elements inside here than we have the dimension of E, which is 2. So clearly they can't be. We have linear dependence between them. So, but the idea of linear independence is quite useful. So we're now going to introduce something called a base of a root system. And that you can kind of think as being like an analog of a basis for a vector space. So it should be something from which you can generate all of the elements of your root space as linear combinations. Okay, so the set itself, this capital pi, this itself should be a basis of E. So this is a basis. It's going to be some linearly independent subset of the roots. And in addition to that, it's not just any basis, because we wanted to remember somehow the structure of the root system. And for that, it means that we want every root is going to be, basically these root systems are very much like integer structures based on integers. So we would want then that while this pi here is going to generate the whole space as a real vector space, we would like it to generate the root system in an integer sense, because these are the heart of what a root system is. It's the symmetry together with the fact that it's this discrete integer structure. So you want then that this base is going to give you all of the roots, but in an integer way. So that's not, we want a stronger condition than the roots are going to be contained in the integer span of pi. We in fact want a positivity and a negativity in there too. Kind of reflecting, if you remember, that the only roots, reflecting the definition that the only roots, multiple of a root that are going to be in there are plus or minus 1. So there's very much a positive and a negative part of root systems, and that's captured here by the notion of a base. So we want it to be some integer linear combination, but the integers have to be either all greater than 0, greater than or equal to 0, or all less than or equal to 0. Okay. So this is the notion of a generating set. If a basis is a generating set for a vector space, you have a notion of a generating set for an algebra, a generating set for a group, and so on. For a root system, the generating set is a base. These are the conditions. And we call the elements of a base, we don't call them base elements, we call them simple roots. Okay. Now from this, as you can see, it follows basically immediately from the definition, the positive integer span of your base, or the positive integer span of the simples, that's going to be equal to, we call that the positive root system. And we denote it by delta plus. The negative root system, let me write something in here again. No, the negative root system, which we call just which we're going to call delta minus, that's just defined to be minus of this. But of course, you can see that that's just equal to the negative integer span of the base elements. It's just maybe a little bit more concise way to write it down. And here, this should be minus. And we see that from the definition that any root is either a positive or a negative integer combination. It means then that this, if we take the union of the positive and the negative, then we get everything. You got no mixed terms inside it by the definition of a base. So then we can break our base system up into these positive and negative parts. All right, so let's clear that. Now, how do we construct a base? So that's it's fair enough to introduce a definition, but do such things actually exist? You introduce the notion of a basis for a vector space, but then you have to prove that a basis always exists. Okay, well, in fact, it does. Number of different ways to prove this. We're going to show that one can construct it from a choice of a thing called a regular vector. So let's recall that this was the symbol we used for the hyperplane that was perpendicular to any root vector alpha. Going to be all of those elements in the vector space E that were perpendicular to this. Now, we want to take the union of all of these hyperplanes, okay? Just the set theoretic union, no linear span, just the union of these things considered sets over all alpha. Now, an important point, and you should think about this, is that such vectors are going to exist, assuming that our dimension is greater than 2, but then greater than or equal to 2. I mean, if it's dimension 1, then it's clear that we have a base. It's just going to be the pick the one of your root vectors. You're only going to have 2. Pick one of your root vectors, and then it has a base. So for the construction of a base, we're going to assume that we have dimension greater than or equal to 1. And in that case, if you take a finite union of hyperplanes, then you can't cover the entire space. These hyperplanes are not big enough to do this. So you take the union of them, that means there's not everything, that means there will exist something in the complement. And any such vector is called a regular vector. And we're going to use these regular vectors to construct bases.